Oh, there we go.
Oh, much better right there.
Oh, wow. How about that?
Your voice got deeper there, too.
Amplified.
That's my radio voice. All right, so you guys, if you're here, you're probably here for those guys, not me. But I had the microphone now, so I'm going to talk for a second. Oh, yeah, you are. You gave up. So I'm a total nerd that loves engines and tribology. Tribology is the study of friction, wear, and lubrication. So what we have on the screen here is a test we were running at the tribology lab at Southwest Research Institute. That's a section of cylinder with a ring against it, so it can cycle it just like it is in an engine. And we can control the speed, we can control the load, we can control the temperature, and we can look at it under a 3D profilometer. Afterwards, we can analyze the used oil. It's like super, super cool. And the only thing cooler than this test by itself is to watch it run in slow-mo. How dope is that? This is happening in your engine all the time. Not that slow, no. But it's kind of cool to see it in slow-mo like that. So anyway, this is the kind of fun stuff we get to do. Thank you guys for buying parts, because we appreciate it, because you buying parts lets me go play and do cool things like this, just so you know. In the end, yeah, it gets better. Because, wait. All right, so we're still a couple of minutes early, so I still have time to kill that's on my time, right? So if I can drive my laptop from the other thing. So there's some pictures of the wear scars from that same test. But then when you get it into the 3D profilometer, that's the unrun area as honed. That's the run area. Obviously the red spots are the high spots. The green spots are the low spots. The blues are the valleys. So when we're talking about honing, we're talking about RPK, RK, RVK. The red is your RPK. Your green is the RK. And the blue is the RVK. How cool is that? You can actually see it, right? So much better to see it than look at dumb numbers. And then as a tribologist, oil film is related to speed. Think about a water skier. The boat's going fast, the skier's on top of the water. You go in the no-wake zone, what happens? Boat slows down, skier starts to sink in. And boat stops, skier's in the water. You can see that on this trace. That on the far right side at mid-stroke, there's more red. And as it goes towards ring reversal, because what does that ring have to do? It's got to stop to turn around. You see it, and this one's not blown up enough, but at the very end, right where the ring stops, it's fully green, and there's actually a little cradle there because the ring's barrel-faced. It was so stinking cool. So that was doing it one way, right? So we'll call that the traditional way of doing things. That's an uncoated ring, regular oil, regular hone, and the one next to it is doing it my way. Plateau finished, coated ring, and I'd use my oil. And where does it stop? You can't tell. It's so little wear. So that one produced a total of 20 parts per million of iron in that test. The previous one produced 83. So we changed the wear by a factor of 4. Yeah, that's fun stuff. I think it's time for us to start our real talk now, right?
Yeah. Well,
enough of me geeking out on my own.
Hey, but like
they gave me a stage and a mic and a laptop.
Well, like
Whoops.
Even though this isn't part of our talk, this is a system setup because you can't run the surface finish. If you ran the ring from condition 2 in the surface finish of condition 1, it'd be horrible. If you ran the surface finish of condition 2 with the ring of condition 1, that would also be horrible. As a system, you had to, if you're going to use that coated ring, you've got to have a better finish before you start.
Yes.
If you're going to run the worst finish, you've got to have a ring that breaks in the surface. So the whole idea is that none of these, a lot of times what we get is people come up and they talk to us like, what's the best component for my engine? And really, it's not. That's not the whole. This whole presentation is about. That's not the question you should be asking. Our presentation is try to talk to you to think about every component in your engine as part of a full system.
Yep.
So today we're going to talk about developing engines as a system.
Right. And I got to find out a way to switch this on. Hold on. This is my mouse being lost.
Don't hire Lake as an IT guy.
I'm bad at that, obviously.
He's a heck of a PR guy, though.
PR guy, awesome. If you need a nerd, you can either buy or rent this nerd over
I'm
here.
a good one for that.
He is available.
But don't hire me to run your laptop.
Right.
I swear I can't see the mouse. Can someone see the mouse? Because I can't see my mouse anywhere. Oh, here it's on this side.
Just click, yeah.
I think the problem is the screens were backwards. That's right.
Yes, you've got to figure out the way that screen is that screen and this screen is, yeah.
I'm dyslexic anyway. Hey, guys, that's us, by the way. So I am Lake Speed Jr., and that is...
Yeah, I'm Billy Godbold.
And I am Ben Strader.
All right, so...
And oddly, we're actually all friends, too, so in real life, so not just up here for this stuff.
Right.
Well, we tend to nerd out together, you know. I mean, like, you get excited about that stuff, and we get excited about other stuff, and we just end up on the phone all the time. So.
Nerds of the feather flock together, so we're up here on the stage. So anyway, fun. So like Billy said, this is all about finding that hidden horsepower through the synergies of systems, because it's not about just individual parts, it's how those parts interact with each other. That's where that next level comes from.
Yeah, I mean, so many times, like, we talk about how the engine is really just a series of interconnected, like, dependent events. And you can't just make a change to one part without it affecting a bunch of other things. So often we find ourselves chasing the what just happened, right? I thought I was going to change this thing, and I did, and I thought this was going to happen, and all these other 6 things changed. And so we find ourselves always pushing and changing, and so there's never really an end to that. It's more of a circle than it is a straight line.
You know, and I just realized that by dumb coincidence, I was saying the example was cylinder bore surface finish in ring paste coatings. That was a complete accident, by the way.
This whole presentation was done before you had that.
Yes, and this is the practice run, by the way. We've never done this together, so you're the victims or guinea pigs or whatever.
Billy and I have a technical term that we use all the time. We call it getting laked.
Okay,
so when
y'all are getting laked right here in front of everybody else.
Yeah.
Well, I guess you are too then.
Yeah, and honestly, about 3 or 4 weeks ago, so one of my friends calls me and he talks about this great conference that there's going to be, and he sends me a link to it, and I said, "Oh, I want to go. That sounds great. I want to be part of it." He's like, "Dude, you're presenting."
All right, so let's talk about the first thing that I think is kind of the backbone of a lot of this is material technology, because if you think about it, that's probably the biggest change in the last few decades is when I say material, not just the alloys themselves, but also the coatings, surface finish, all of these things together. What we're doing with that material is really give you that foundation to work from. I mean, obviously, Billy, you've seen that with the camshaft stuff.
Right.
Valve train.
Right. But for those who don't know me, my background before I decided to join the circus of motorsports, I was a nuclear physicist. But we did a lot of material technology at Florida State. And so I love, if I ever had to get a real job, it'll be as a metallurgist. And every failure actually starts microscopically. It starts down at the atomic level. And so what you see is we do all these crazy things to try to make materials better and better and better, and they work awesome and everything. But there's a whole division of engineering called surface engineering. And so there's the tribology that you're trained in, but also surface engineering. You have to look at what's going on at the very surface area where these things are contacting. And so all of this processing on the camshafts, we were looking at RA, and that was how you go, okay, the surface is RA. Well, I worked with our friend Mark Marburg, and you guys know Mark as well as I do now, but he's a great guy, and he helped me understand that RA really wasn't very important, that it was a byproduct of what was important. Like we look now at material ratio, RMR. And so we look down at 10 microinches and 20 microinches. What's the material ratio? And then not only material ratio, but the contour. So if you look at if you were able to look at one of the camshafts that Comp does for a roller cam at really high resolution, it's at a crown finish. also waviness about it. So it's not just roughness, it's the contour, and there's just different setups that you go. So a lot of things that we've done historically over 10, 20, 30, 50 years, we may not be taking the actual measurement of what we really care about. We're taking a measurement that's something's related. And what we've learned to do over the years, and what you're going to, is start measuring what we really care about.
Oh, exactly. 'Cause I think your point about the alloys was a great example that you could take a cast iron cam and you could have these issues and you need to make it stronger. So you go to a better alloy and you keep going to better and better alloys. But if you're not also at the same time changing that surface geometry, that if it was flat on that roller cam, it actually was bad because now the dynamic forces would push down. And like you said, those big pits that you would see on your camshaft lobe actually begin under the surface where the grain is actually dislocating. It shows up as a pothole on the top, but it began with a subsurface crack way down underneath.
That propagates up.
It goes up. So yes, you can make a better material, but the problem was contact load. That's what actually causes the dislocation to begin with. So if you had a higher material ratio curve, better load carrying capacity, a poorer steel could actually do a better job than a great steel with poor surface finish. It's the combination of the two.
And that's one of the things, like I was talking one time, for a few years I did a lot of steel development, and I was super proud of myself. And so I talked to one of my friends who's a PhD, really good guy over at Cummins, and he's over their valve train setup. And so we're talking, and I'm like, hey, look, what metals are you using? And I'm like, he goes, well, why are you asking? I told him, well, I've gone up from 220 KSI to 280 KSI ultimate tensile strength, which is a huge change in steels. That's like a big deal. The worst steels are around 100 KSI. The best you can get is around 300, maybe 310, maybe 330, but that's about all you can get in steel. He goes, well, what if I told you that I tripled mine? And I'm like, well, you can't. There's no, if you're at 200, there's no 600s. And he goes, well, what's your material? What's your bearing area? I didn't know what he was talking about. And he goes, look, Billy, if I'm applying this load, if you are running 30% bearing area and I'm running 90% bearing area, that 90% bearing area to the atoms in the lattice on the surface, I'm putting 1/3 the load on those atoms. So that's the whole idea of trying to spread that load out better. You can do things by system design to spread loads out better, that you can do more on that than you could ever do with the materials, because there's just a limit to how good materials can be.
Right.
And one of the things that people don't get on steels is like, you don't ever change the stiffness when you change steels. Your mild steel has the same stiffness as the best tool steel grade or super alloy you're going to get. There's not 5 or 10% change. So when you're going, oh, I'm going to use this material on a rocker arm, well, what a really good, like if you're at Jesselyn, you want to use a really excellent steel on a rocker arm, that doesn't make your rocker arm any stiffer. What it does is let you make sections thinner so that you can do more stress in that area. It doesn't make it any stiffer.
So a really great example of that, we see a lot of times where we're so focused on trying to get stiffness. And so we'll find a part or a material, like some of these pictures here you have, like you and I started talking about some of these, go back one for me if you can. Some of these more exotic metal matrix composites that we've been messing around with. So a lot of the stuff on the screen there looks like aluminum, but it's metal matrix composite. And we spend so much time going, I want a stiffer part, or I want a lighter part. And like, for example, I see the retainers there that we did a bunch of spin trend testing, and it was like we started out with this material that is as stiff or stiffer, but much lighter than the titanium stuff we'd been using. Well, we made the first iteration and design of these retainers in the same shape and dimensions as what we had for titanium. So size for size, we were orders of magnitude stiffer, and I think we were probably somewhere in the order of 40% lighter than the titanium it was replacing. But immediately when we started to spin trun test, what we found is when you got that part stiffer, the energy in the system didn't go away. We just moved it somewhere else. And so all of a sudden you're like, cool, that part's not failing anymore, but all of a sudden this other thing is failing. And we saw that with, just on the corner there, you can see those kind of carbon push rods. We did a lot of testing in that, and the materials and the finishes on the surface of the tips of those. And at the end of the day, we kind of got to this point where we're like, well, define better. As far as my whole system, yes, technically I can give you 3 metrics that we can say this part is better, but my system didn't get better because there was adverse reactions from other things. And so this talks really about how do we integrate some of these technologies as a system and end up out the back with a better engine. It's sometimes materials, but often we have to think about the way that we're using these materials and the dimensions, like you said. If it's stiffer and I can make the mass lower, then I win, right? But I got to think about where else that energy is going as well.
Right, and you could even think about like that retainer. If it's 40% lighter, can you go to that next slide?
Yep.
Just real quick. This is talking about system stiffness and stand stiffness and everything like that. And people don't really think about it, that like you could take your hot rocker arm and fix it and put a load on your valve, and you can watch the deflection of the tip, but you can also watch the deflection of the stand. And like that stand stiffness normally isn't costing you any mass anywhere. But like when he said, when he makes that retainer lighter, that means when you're opening and closing the valve, there's going to be like, thousands of pounds of load on the tip of that rocker arm. Well, that's going to flex the rocker arm, it's going to flex the stand, it's going to flex the push rod. The whole system is going to start bending around. So as soon as I take, and camshafts are really weird, valve trains are really weird, because if you had whirled enough in time, you'd really want a small aggressive camshaft at low RPM, and you'd want this big poochy cam at high RPM. What happens is in life, when you have stiffness issues, the worse your stiffness is, the more you get the opposite. The camshaft shrinks. Like at EFI University, they're measuring, on their spintron, they're measuring dynamic durations. And you'll see almost all camshafts are going through all this flex, between the cam flexing, the push rods flexing, the rocker arms flexing. You'll see normally, if you looked at from like 5,500 to 8,500 RPM, over 3,000 RPM, you're going to see about 15 degrees of duration loss.
Almost always at a minimum about that. So
Right.
A great example is we have one with about 700 pounds of spring force, right? So that's 7245. Great
Right.
spring. 200 on the seat, 700 open, which is not by any stretch of the imagination a big spring.
No, really light for the application.
Yep, and even in a system with a steel shaft-mounted rocker arm, a really good, 24 to 26,000 pounds per inch of system stiffness, we will start out with a camshaft that's, let's say, for example, 280 duration at 50. Well, by the time you put 20 thou lash in it, it's 270-ish, right? So we look at what the duration is at, say, 1,000 RPM, and that becomes our baseline. And what you see is as the engine speed increases, the forces in the system are increasing, and so you're getting more bending and more deflection, and effectively you're getting a smaller camshaft. And so it's a great example of a systems approach where you go, I just need a stiffer push rod. And you do that in real life, and you go, well, if I didn't have a spintron to know this, the number one complaint you get when a guy increases the push rod is the engine made less power. Well, yeah, because now your camshaft's too big. And so we got to rethink the whole system rather than the individual parts and the components of the system.
Right, and then there's some weird stuff, because like say the valve spring goes into surge. If you have a spring that goes into surge, you'll be looking at that plotted duration versus RPM that's been going down really linearly, and you'll see just drop 5 to 8 degrees in 100 RPM. And that's because the surge has happened, and that surge has gone and tried to put all this extra load into your system. And so everything, and if you're not looking at things as a system, you'll just throw something in there and think, oh, well, that was bad.
Or this part is better.
Right, and neither one of them's true. It's just something was working well. So it's just and I wish we could figure out a way. This is something that I've been learning over 25 years. You spent the last 5 years or 10 years on it. We're just learning on the thing. So we can't tell you your perfect thing for everyone in this room. But hopefully what we can give you through this presentation is a way of looking at things in a totally different light that I didn't do at first. I used to run around this thing and I go, well, I can get 5 horsepower here, or 10 horsepower here, or stuff like that. And it's really a different setup. So
Exactly. And obviously the system stiffness is a big part of this, of making sure that everything's working together and the things are bending where you want them to bend and not bending where you don't. So the timing of all the events is the same.
Well, the other thing, like say if you have a rocker arm that's bending a whole lot, and you go put a stiffer push rod in. All you've done is add mass because that wasn't your Herbie. You know,
Right.
that book, The Law of Constraints, it talks about all the different systems. Like if one part of your valve train's really not very stiff, there's nothing you can do in the rest of it to make it better. So that's back in the whole thing. I could throw, if I have a problem in the stand or a problem in the rocker arm, if I try to address it with the push rod, it's going to tell me a lie.
So let's talk about the more common application, Billy, which you'll be familiar with. One of the number one things that I see people doing all the time is you go, hey, my valve train's out of control. So what do? I'm going to put more spring in it. That's like the most common thing, put more spring.
Yeah.
Well, if the reason the valve train was out of control is because the spring force was adding to the bending and deflection in the system, all you're really going to do is make it worse. Now, oftentimes we can be so massively oversprung that we hide it, right?
Right.
We mask it.
The gorilla approach.
Yeah. But when you actually start to look at the data, you see, gosh, I'm wasting all of this energy in bending the system, and it's just sort of compounding. What we're doing is we're building a diving board. And there's some RPM, when you get there, that diving board is going to be coming back the other way. And so you talked about it losing, all of a sudden like that. Well, we see the same in lift, right? Like literally in less than 1,000 RPM, less than 100 RPM, it'll be like a light switch where you have a valve train that's totally happy at, let's say, 9,400. By 9,500, the thing's got 50 thousandths of bounce off the seat. So we get the bounce so bad that the bounce has its own duration number sometimes.
Mm-hmm.
It'll be off the seat for, 50, 60, 70 degrees during the compression stroke, and it's like, well, geez, now I understand. It won't make any power with the valves open.
Right, and then you get the guys that are running, like forced induction, so common today, that sometimes you can hide that with enough turbocharger. And so all of a sudden you're doing some horrible things in your valve train, and you're still going pretty fast down the track. Sorceress. I didn't say that out loud, did I?
No.
And you think it's really great, but man, I'm changing springs all the time. This thing will not go down the track consistently. One time it does this, one time it does that, and all of a sudden you cure some of that by that whole thing about looking at everything together, and it can be just so much better. And one of the things that, if I could talk you guys into anything, if y'all measure the stiffness of your valve train and maybe just start weighing your valve springs like you weigh your valves, to think about that's mass too. So just think about all of that stuff. Everything in there's mass. Some people go, hey, the lifter doesn't matter, the push rod doesn't matter. Well, it doesn't matter as much because all it can bend is the camshaft. But it still matters because when that, you could think about when I'm designing a camshaft, it's like I've got a gas pedal over here and a brake pedal over here. And so, I'm hitting the gas to get everything moving, and that energy's going into the valve spring. And then when I stop it over the nose, I have to slam on the brakes. The only thing you have for a brake pedal there is the valve spring. If the push rod has mass, it does, and it's got velocity, it does. You got to have some force to turn it around. And so that's the whole idea, is thinking about, well, this is mass too. So I don't want to just throw push rod at it if that's not the deal. And sometimes we were so oversprung that it seemed like that it was always good to throw more push rod at it. But that was because we had the Gorilla spring in it, not a spring that was lighter and well developed for it.
Well, and like so many things in the system, we've done back-to-back testing in the same day where you go, I'm going to start with a 3/8 push rod, I'm going to go to a 7/16, then I'm going to go to a 1/2 inch. And you often find where it's great to have the stiffest push rod on the planet, but again, all we did was take that energy and move it to the next thing in the system. So, we used to talk about, we need bigger cam cores. Well, if that's not the thing in the system that's bending, it's a nice to have, but it's not really fixing the problem. It sometimes even makes it worse.
Yeah, everybody had gone over to 72 millimeter cams. Mike Edwards won his last Pro Stock Championship with a 60 millimeter.
Yeah, 60.
And that car was fast.
Yeah.
So, you don't always have to be, just because a little is good doesn't always mean more is better. Now, I wouldn't recommend anybody start Pro Stock today with a 60 millimeter cam. Don't hear me wrong. But, he had a really well-developed package.
Yeah, it's definitely the bigger isn't better approach.
Yeah, not always. Just be careful.
Well, and one thing you can use to apply to help reduce some of that mass, I'm thinking about the Engine Performance Expo, Ben, engine, where here just recently, by the way, it's January 13th, 14th. You can watch it on YouTube.
Shameless plug, right?
Yes. Did I do that? Yeah. So last year, with that engine at 8,100 RPM, we were in full valve float. I think one of the valve bounces was about 50 to 60 degrees of duration.
At least.
At 8,100 RPM. And then we actually went to stiffer push rods. We spent a lot of time with the Spintron trying to see if we could make more RPM. Then we realized it wasn't, the system stiffness wasn't the problem. It was actually just mass. Just the total amount of mass hanging out here in space was the issue.
Yeah, if the only thing we were judging the valve train by was the stiffness, by the time we changed all of the, the original aluminum rockers we had over to the, the BSR system with the shaft, man, we were thinking this is going to be amazing. And we went back in and we did the test and we're like, man, it's sort of the same. And I remember
Right.
calling you going, man, this can't be good. It's not stiffer. And you were like, just go run the thing. Don't be dumb, and like, trust me, it's going to be better. And what did we gain, 1,400 RPM or something?
Yeah, so we would go full valve mounts at 8,100 RPM. We were making pulls all the way to like 93, 9,400 RPM.
Yeah.
Everything's smooth as silk.
Like until you got tired of doing it. Like you couldn't break the thing.
Well, the problem is it was so far beyond the power curve, it was like, oh, this thing sucks, but
which is
think about
code for it needed boost.
Oh, yeah, but before we put the boost to it, then it got a lot better. But you think about it, you had this big aluminum rocker with this heavy roller tip out there in space. When you go to this smaller steel rocker, we're back to where now surface finish, there's no roller because there's a tip on it. That we can coat that tip so we can reduce friction, so we can have more contact areas, so we can have less friction. We can begin to apply the coating technology to help make up for some of the smaller materials where you could be increasing load and increasing friction. You can think it back to the system approach, that if I rethink it this part and I can use materials, we can use coatings, we can use surface finish, we can make lighter, stronger parts, and that less mass will actually.
So going back to the picture of the retainer, I mentioned that we started out with that metal matrix composite. Mm-hmm. It's an aluminum silicon carbide material. It was originally designed for Formula One, and then it was banned, and so we kind of picked it up and started making stuff. And originally, we were making the dimensions of the part the same as what we had for titanium. And we found some areas where the spring tips were basically jackhammering, if you will, into the radius there on the step. So we had to rethink our approach there. Does the dimension of this material need to be the same? And then we went to coatings, and in fact, we went to IHC and did some of the Cassidium coatings, and we saw huge improvements by taking two technologies and putting them together, right? That systems-based approach. And it allowed us to rethink, does the retainer need to have the same shape if it's not the same material? So that was a great example of using a coating to our advantage.
So the next thing we got to do is you're going to do all this, you're going to have to measure things differently. And when we start measuring things differently, we got to start thinking differently in terms of scale. So when we're talking about a micron, how big is a micron? And Billy, you tell us. You sent me this slide, so you go for it.
Well, I mean, this is one of those things that on one of our surface finish plots, our full scale is plus 100 microns to minus 100 microns. And sometimes you'll see the little something with the dress and the CNC, and it'll make this big blop on the screen. And, so my full screen's 200 microns, and you see something that's like 20 microns in there, and everybody freaks out, and you're going, hey, guys, let's really look at what a microinch is. And so I have this up on the board there. So a human hair is 4,000 microinches. The exhaust smoke particles they see from diesels, they are on the order of 80 microinches. E. coli is 40 microinches. A red blood cell is 280 microinches. So when you have to tell somebody, hey, that blip that you see on this screen, that whole screen's not as big as a blood cell. Your human hair would be big as the room at this scale. So, and you go, what we're seeing is something that's about a quarter of the size of exhaust smoke. And then they go, oh, so that's not so bad. Well, why do you have it zoomed in so much? Because I can, Because
it looks cooler that way.
And one of the things you find out is you start measuring things and how sensitive internal combustion engines are. There are things that you can just as you start seeing, you go, there's no way this matters. And absolutely it does, because all the interactions are at a microscopic scale.
Yeah, I mean, think about how many of you cylinder head guys out there, if you've ever changed the valve seat by 10,000ths of an inch in width, it makes a difference to the airflow. So the only thing that I would say is, like, the better we get at using like equipment and the finer we're looking at stuff and the more we're measuring, the more miserable we become, because everything's junk. You
Right.
start finding all these problems that we didn't know about before. and sort of iteratively fixing what we know is wrong and then moving to the next thing and finding the surprise that we didn't know was wrong. It really like gets more scary the closer you look at some of this stuff.
No, it really does, but then it gives you a chance to get better. You know, he's got one of my favorite Scooter. Scooter has about 10 things that he's told me over the years that changed my life. And one of them that definitely did was, you know, he totally came up and he didn't say it exactly like this at first. He looked at me and goes, Billy, you're trying to make ball bearings and measure it with a wood rule. You know, and he basically, your ability to manufacture something is completely and totally limited by your ability to measure it. Like if you're honing blocks and all you have is an RA test, man, you may be doing a great job, but you're guessing. You know, I love you, think you're great, you're awesome, but you're guessing. You know, until you can look at things at a better way at what's really mattering, you know, what matters to your system, you know, yeah, that's the whole thing.
Which is why you got that.
Yeah, that's why I got that. Now, what's funny is that usually when I got a new toy at Comp to measure stuff, we wouldn't ship camshafts for a week, and then Scooter would lay hands on me, and we'd figure out a way, and I'd get inspired to figure out how to let things go. But, you know, every time you measure something, just like you said, you're like, oh my goodness, you know, we got ag holes, we didn't ship a camshaft for a week. We got this thing, we didn't ship camshafts for a week. Yep. But after a while, you start learning how to make something a whole lot better. And that bottom scale there, if you look at the top, there's 3 plots on there. The first scale is looking at the whole contour, taper, everything like that. The second scale looks at the crown on the lobe, and the third scale takes the crown out, looks at the surface contour that the lifter's riding against when it's loaded. And being able to look at that, man, that probably, and I was telling Mark that ability to use that Zeiss skidless profilometer, to have the Profile Master software that Mark developed, and actually stole a CM out of Found a deal to make the base and everything like that. Yeah, that was kind of fun.
It was my favorite tool because I got to do this with it.
Oh yeah, but it's amazing when you start looking at that bottom scale really is plus or minus. That's smaller than a red blood cell.
So those are flat tappet cam tests when we were developing the GP1 oil, and those are wear scars. That big yellow area is the wear scar between different oils. And you could actually measure that with a profilometer and actually see, well, what does it do? Because maybe over the nose, it would average out to be pretty close. Mm-hmm. But then when you actually zoomed in and across the nose and you see this wear scar, it's pretty crazy. And of course, the great part is being a flat tappet cam, it's not flat, right? You can see the taper in the lobe there from left to right. I know, by the way, that little round actually matches the crown of the lifter almost identically. The one that's really good, that's really low, it was pretty awesome to be able to put the profilometer over the crown of the lifter and measure the crown of the lifter and then measure it reverse on the camshaft as it actually broke in. Like, that's kind of crazy, right?
Yeah, when he says close, he means like 59.1 inches on the lifter and 59.15 on the camshaft. I mean, like really, really close. The idea, you know, there's some things that you hear from the old guys and you think they're wives' tales, like, oh, camshafts and lifters break in, and you're like going, no, they don't break in, and everything like that. Then we tried different things, and we found out that, you know, that the camshaft literally does wear in to match. And after you've seen it, you can look at it and see it.
It has its home.
Right.
It literally finds its place.
Right. And if you could have really good lifters, you could probably swap them out on different lobes, but that only works if you knew every lifter had the same radius. Yeah. If it doesn't have the same radius, that's where you get these guys going, number 16 lifter has to go back into number 16 lobe on that block. Yeah, because those have all worn in together.
Yeah, they've matched up identically. And the same thing kind of goes for surface finish for really even anything, but cylinder honing we do a lot with. And Mark actually has a new version of his software, which we've been displaying the last couple of days, called Trace Boss, where it lets you go beyond just the numbers. You know, anybody that has a profilometer that's been honing and trying to trace the numbers, you know, as machinists, it's ingrained in you, in all of us, right? If there's 3 decimal points, we're measuring to the thousandths. So we're going to target, we're going to machine, we're going to get to that thousandths. And now you got this profilometer that says, hey, 8 to 12 is fine. Anything in there? And you're like, no. If it's 13, well, I got to fix that. No, you don't need to fix that. The picture can tell you more than you need to know. And you can see that. So when we're talking about our VK, that valley, that's the blue area. You can actually see it with that software. So that's one great thing, is you can begin to really see your material ratio curve, which is on the far right-hand side. You can see what's going on so much better. The numbers are helpful. They're kind of your sanity check. But the picture, because if you think about it, those numbers are a numerical representation of the picture. If you can actually see the picture and you see it on the same scale over and over again, it's so much more valuable than numbers alone. So that's part of it. And I actually did include this in here. I can't help myself with this one. It's my favorite thing ever. You can see the little green trough, can't you, right there, right to the right of the red. That's where the ring stops. You can see a little bit of a barrel shape in there because that's the barrel face of the ring where it stopped. I can look at that like all day and just never get bored. Then Mark did his picture the other day. He has a 3D section of an alusil bore that can just spin in 3D. And you can see the little silicon nodules. Oh, it's so stupid cool. I could sit there and look at that all day as well. But that's why, Ben, tell them what we're looking at there.
So if I'm not mistaken, that's the ring from the new Godzilla engine, is that right?
Yes, that is.
We got a bunch of those engines in at the shop and kind of started with a totally stock one, and we tore it all apart. And again, the first step is to measure. And so among the various parts of the engine, we have this digital microscope here, which is another one of those tools that I was saying, if you're not careful, it makes you sort of like hate everything. And the first thing I would say is it's live. It's a digital camera. That's microscopic, and you can zoom in or out. So on the first day that you play with it, you realize that you didn't wash your hands enough because they look terrible, right? But after that, what we're starting to do is look at various parts from bearings and retainers and rings and springs. This is the face of that Godzilla ring, which was, I didn't know about this beforehand. Did you? When we discovered that they were doing this with the
I didn't realize that with that engine they were using a moly-filled top ring, because that's what you're seeing. Those are two rings stacked together.
Moly fill. So if you look at that ring on the top, what they did was they went into the face of the ring and basically cut a trench. So that's why it's darker colored at the top and at the bottom of it. And then they filled the trench back in with moly. So it's almost like the benefit of having two different materials on the face of the
so it's a steel ring with a moly face in it. And then all those little pores is what holds oil. So when you have a moly-faced ring, it's very forgiving on surface finish because you don't need those valleys to hold the oil because the ring's a sponge. Of course, the only downside to that moly-faced ring is it's a different material than the ring. So if you're running big boost, you're running nitrous, it tends to crack and flake and break out, and then bad things happen.
That ring tends to be much more sensitive to the tune-up simply because if that moly's a hard material. So if you get into things like detonation or high loading, that stuff wants to fracture. And so when it fractures, then you have adhesion issues. It wants to come out of there. Those pieces end up in the rest of your ring grooves. Obviously, the ring doesn't want to rotate, so it's a little bit easy to damage that part of that ring. But it has lots of.
And what Lake was saying too is like every material. So when you make a bimetal part, when you've got two different materials, they never have exactly the same expansion ratio. So what happens is when the steel expands and the moly expands, they expand at different rates. So they create all kinds of stresses in there.
Exactly, which is why the bottom one is actually just a steel ring with CRN, so chrome nitride. No different than what's on your titanium valves. What makes that titanium valve look shiny and chrome is chromium nitride, which is not the same as hard chrome. So if you've got chrome-faced oil rails, that's hard chrome, just like a bumper on a 57 Chevy. Which is why it's lumpy and peaky, which is why when you drag it up and down the cylinder bore, if you have a high tension oil ring, you see all these streaks. That's the high spots on the chrome. That's where it comes from.
That was the high spots on it.
Yeah, you're right. Yeah. I'm not good at IT, and I'm not good at English either, so I have my grammar correction over here.
It used to be the
I'm a race car driver's kid.
Now,
come on, give me a break.
The high spots are gone there on the cylinder boards.
All right. So the other piece we can do is oil analysis, which, again, if you guys know me, you know I love oil. And oil analysis is absolutely my favorite topic within oil because I'm kind of oil brand agnostic now because I want to be an independent guy. So the best way to do it is oil analysis because I believe in chemistry. The chemistry is what matters. How do you know what chemistry is? The oil analysis. It's going to tell you what's in the oil, and most importantly, it's going to tell you what it's doing in your engine. So, for example, those bearings right there, we were doing one of our engine rebuilds, changing out piston rings, and me and Dan Brewer from Shavers got in a hurry because we were running out of time, and we didn't clean it up as good as we should have, and we introduced some trash in there, and that trash started to score that main bearing. And guess what? When we did the oil analysis after that run, because we always do oil analysis after every run, you can see 29 parts per million lead. That's from the lead overlay in that bearing. So when you see an oil analysis report and you see 30 parts per million of lead, well, what does that mean in the engine? It means that in the engine. Yeah. Is it gone? Is it failed? No. Is it going to? Yes. Eventually it will. So
this is another great example, though, of using the oil analysis as part of your system, right? Like so many times we think when we build the engine, it goes off to the customer and then you're done with it. You just don't see it anymore. But the reality is, if you've done at least a fair job, it's probably going to come back to you at some point and you're going to want to tear it apart and freshen it up. And so, understanding what's happened to the engine, this oil analysis report is a great example of the total system working together, right? So I can see things in my tune-up from the oil analysis report. You can see you didn't get it clean enough. There's so many things that the oil analysis tells us about the engine over the long term that it becomes another part of our engine, right? It's not just an oil report. It's literally the thing that drives our decision making on the clearances, tolerances, and materials that we choose for the next go around.
And when you couple it with the reverse blueprinting, using the microscope, using the profilometer, when you take that engine apart and you remeasure all those used surfaces and say, okay, this is what it was new, this is what it is used, and I take those visuals, include the oil analysis, now I have a complete visualization of what happened to that engine. I have a much better idea of
I think yesterday, Randy was giving his presentation with Dan and those guys, and one of the things he said is the most important guy in the shop is the guy in the teardown room. Yes. We talk about reverse blueprinting our engines all the time. Everybody's familiar with blueprinting the engine and putting it together, but there's so much more to the story when you take the engine apart. The last thing I want is the new guy in the shop taking stuff apart, scrubbing parts, and throwing them in a bin, because then we don't know what they look like and what happened, and we don't get the oil analysis report. It's the same thing. That's all part of the total system. In my shop, I tell everybody all the time, we're not an engine shop. We don't have a lot of customers. We don't sell a lot of engines. We do R&D. So what that means is the difference is we work on the same engines over and over again. So we do a lot of engine work, but on the same engines. And so after a while, you become intimately familiar with what those parts should look like, what that chemical report should look like. And so it's almost like if you're not looking at those things, you're giving away a bunch of information that you could have had for free.
Well, I remember Mark Cronquist said that the biggest thing that has slowed down their learning curve with their desert off-road truck engine is that those engines run thousands of miles and they only run a handful of races a year. He said, so our learning process is so much slower because back in the Cup days, when you had practice motors and qualifying motors and race motors, you could literally be looking at 10 engines a week that you built, you ran, you tore it back apart. You learn every time you take it apart. So if you build these 10 engines and you don't see them for another year, it takes you a lot longer to learn than if you're seeing 10 engines every week.
Think about that Engine Performance Expo engine. We finished it on the first go around, and we ran the thing on the dyno, and the very first thing we did was pull off the dyno and take it apart.
Yeah.
So that's such a rare thing in our business or in your guys' business, where the goal is to make the engine go away so you can get paid. Our goal is
you don't see it again for a long time.
Yeah, we don't want to see it back for a long time. Our goal is to run it and take it apart and look at it, and that's just such a different way of thinking about engine stuff.
Yeah, I don't think this would be, anything specific to any clients, but most of your NASCAR teams will have a debrief very early in the week as soon as those engines get back from the track and get apart. And I'm sure you had that at Gibbs where you guys, they'll take the engine apart. And so what they've learned from that, and then if there was anything, there'd probably be another meeting later in the week about what we've done to address it.
Yeah, what are we going to do about it?
Before the next week. So, it's something to think about that I don't think that you see the attention to tear down and inspection. And one of the things is when you have a failed part, what I've seen a lot of customers do is they focus on the failed part. And a lot of times I'm looking at, if a camshaft had a failure over here, or this valve spring over here, I'm looking at on the other bank and stuff like that to see if there's something commonly that I can see an infant failure. Because after something's failed and then beat the heck out of them, you look under a microscope, you're like, yep, that broke. Occasionally it'll break and get apart so you can see beach marks and you can tell what happened on the failure analysis. Lots of times it's just beat on stuff till you can't. So, but what you might be able to do is find something, another part that was about to fail on a different cylinder and really examine that. And so, clients will find that weird. Like, I'm like, well, send me the good ones. And they're like, why do you want to see the good ones? I'm like, because the good ones are going to, probably we're going to do what your bad ones we're going to do.
So I'm thinking about our buddy Rod. You were picking on him earlier on the Sorceress project, right? That was a great example.
I didn't say anything about Sorceress, did I? No. He's bigger than me. He beat me up.
Yeah. But that was a great example of like, hey, we got all these broken parts and they just keep doing it over and over. Well, when we started to look at the ones that weren't failed, and exactly. It started to lead to that path of like, okay, what are we doing wrong here, and how have we been trying to fix this problem? And we've made huge changes to the system, not just one component. We didn't just change the camshaft. You remember you made all those ones. It wasn't really just a camshaft. It wasn't just a push rod. It wasn't just the spring. It was all those things together that made that thing work. And we went from chucking parts off that thing at 7,800 to at least Spintron. We can go to 10,000 plus now, Rod. No issues.
Well, and more back to the valve spring thing. We couldn't get it past 6,700 without the boost.
Mm-hmm.
So there was some inherited issue with a reverb. Something was coming back and pushing against the system.
Yep.
And saying 6,700, I'm not happy. And then what happened? It became happy again for a short period of time, maybe until 8,200. And then it went right back into its other things. So there was like different thresholds that were happening to there, and it was telling us stuff. If we listened to it and we didn't know how to listen to it, we
Yeah.
Well, there are frequency. Every valve spring has a natural frequency. So what happens is you run through it, but the higher order term in the camshaft excites this node, and then all of a sudden you go up and you have the next node come up. And sometimes you'll see, if you look at valve motion, you'll see it kind of loft and come back and loft and come back, and it'll do like 5 or 6 times over the nose. And each time this cusp makes it to the nose, it hits and does bad things, and every time it makes it to the seat, it does bad things. So you were just seeing these nodes that you were exciting, just exactly like playing a musical instrument and hitting that same note at different octaves.
We saw this exact thing a week or two ago. We were sharing within our Delta Lambda group. I know some of you guys are in that group, and we were showing some Spintron data where we had a system, and then by system I mean a specific cam lobe, push rod, rocker, spring, right? And the thing at 8,800 was, it was boring. You could do it as long as you wanted. And then about 9 to 9,200, it was a little, maybe 10,000 valve bounce or something like that, which isn't horrible, but not great. And then all of a sudden at 9,500, it was perfect again. Like you could have put it at 9,500, gone to lunch and came back, and it'd still be running. But at 9,600, that's a completely different story. So it kind of was good, it kind of went away, and then it came back, and then it went away, and then it went away really, really bad. So they have this wave that kind of travels through the system.
Yeah, like one year, this goes back a long time to back when Dale Earnhardt was driving for Richard Childress. They had Pocono races that used to be back to back. There's a Pocono race, and a couple weeks later there's a Pocono race. And they had geared the car when it only went like 82, 8,300.
They had the overdrive that back then.
Right, didn't have the overdrive back there. It was just a Jericho. There was 3 speeds, and they shifted at one deal. But then at the main thing, they were just going down the straightaway at 8,300 on that long straight. And what's funny is they blew up 4 engines that weekend between their cars and rental cars. They came back in 2 weeks. They didn't do anything to those cars because there wasn't time except put more gear in the back and turn 8,900 down that straight, and they didn't fill a single engine. So there's nodes, and if you find those, that 67, I promise you've left the engine there, it would puke its guts out everywhere.
Well, I remember Daytona, the tuners, they would go out there and change push rods just in practice, because based on what the speed of the track was going to be, because the engine ran such a narrow range, depending upon what the wind was and how many cars were in the pack and all that, they would change push rods just to move that frequency.
Yeah, they would do that, and then weather would change it, stuff like that too, because if it was nice and cool, the cars went faster at Daytona, and if it was really hot and muggy, and if you've ever been to Daytona that time of year, the weather could be anything.
Oh, in July, it's going to be bad.
Well, July, you know it's bad. I'm talking about February.
Daytona, yeah.
Right,
Yeah,
February,
yeah.
it might be 35 degrees, it might be 85 degrees.
You have no idea.
Right.
But you better be ready for both.
Yep.
All right, so we've kind of talked about this mentality, the systems mentality and thinking, and there's all these different tools we can begin to apply in terms of metallurgy and coatings and surface finish. And then we've got these tools from microscopes to profilometers to oil analysis to quantify what we're doing so we can get ahead. Then we can get into some really fun stuff where you can really find the horsepower. Ben, Billy, why don't you explain what we're looking at? Then Ben, you tell them what you did recently.
Okay, well, what actually drives an engine is pressure in the cylinder. So it's fundamentally, you go, what's making this cylinder go up and down? Well, during the combustion stroke, you create pressure. So if you look at the red line up there, that red line on top is the 100% burn line. This is data that Gary provided from Roush Yates that Doug allowed us to have. This is actually a boosted application because if you look down there at the bottom when it's on the bottom, but basically you see the 4 strokes of a combustion engine here. This is log volume, which is the volume in the cylinder versus log of the pressure. So the 2 purple lines in the back, that's in time the exhaust opens. I guess it's easier for me just go down.
Just walk down there.
Do I have a laser pointer up here? I just walk down here. Okay, y'all can think I'm goofy. I don't care.
Wait.
Does this work?
No.
I'm too old to care now.
Yeah, Ben.
Look at you. Oh, look at you. Yeah. Okay.
Yeah, they're prepared.
See, now
We're just not.
Okay, over there on the wall. Okay.
IT fail 3.
Okay, so let's just walk through this. If we want to look at it, let's take spark right here. And we'll figure, this is the compression line. So everything's compressing here. This is your compression stroke. There's where spark is. So this is heat release going up here. 100% burn here. A lot of times you'll hear about 50% mass fraction burn. That will be usually, 5 to 10 degrees after TDC is where it'll be best. And you see that's where 50% mass fraction burn. This is your power stroke here. As you go down this line, as soon as you open the exhaust valve, the pressure is going to start dropping, right? Because you're getting pressure, that energy that was used to push the piston down is now used to push out the exhaust. So it goes down here. Drops down, comes back. This is your exhaust stroke. Right here, the piston is coming up, the volume's getting smaller, it's pushing the exhaust out, and then you have your overlap cycle here. Now you're going through here, you're pulling the air back in as the piston drops down. That's why this one's below. This loop down here is your pumping loop down here. This is the work that's done. Force over length is work. So this is, when you do log P, log V, this is the work done to push out the exhaust and pull in the intake. Then you come back over here, your intake valve closes, you see the bump right in here. This one you actually could have made this line higher and moved everything up if you closed the intake earlier, but this is a lower RPM. So as soon as you close it, then you have this blue line as it's doing adiabatic compression, then back around the spark. So the power that an engine makes is actually just the cylinder, the power that's working on the piston is just the area under this curve subtracted by the area under this curve. So if you have in-cylinder pressure day like Ben's doing, he can actually tell you exactly how much power this piston's seeing by this guy minus this guy.
Yeah, so if you consider the blue line is when your piston is doing work on the gas, and then the red line is when the gases are doing work on the piston, right? And then like you said, that's your pumping loop on the bottom there. You can go to that next slide if you want. One of the first things that you realize when you can use this data to actually not calculate but measure the power in the cylinders, you find out that if you just do simple, sort of simple arithmetic and take all of your cylinders and add them together, the first thing you find out is that we don't have an 8-cylinder engine. What we have is 8 one-cylinder, unique, individual air pumps that are all doing something different at each RPM. It changes back and forth as you go up and down the RPM. So you start realizing, well, geez, I could try to tune each cylinder to make it not the same as all the rest, but the best that it can be. I'm always going to have a high one and a low one, but I want all of them doing the very best that they can do. And so we learned some very important lessons right away when we started doing this. First was that every cylinder needed not just a different tune-up from the rest, but that the tune-up that it needed was changing all across the RPM range, and in no way that you could easily just predict and say, oh, I think this thing's going to need this. Or they were so wildly chaotic. If you've ever seen the John Kazi video with his finger in the port there, you realize right away nobody can tell you for sure what's happening in there. And so when we're able to do that, we start looking at, okay, so how much power did it make in the engine? And then we look at how much power did the dyno say I made?
Yeah, that's where it gets really fun.
And so all of a sudden you realize, like, wow, there's a lot of, I'm in a pretty high tax bracket over here. I'm paying a lot for this, So Lake and I were working on one the other day, and we were playing, for example, just with oil in the engine, right? And so we had one where we could see the power in the engine, we could see the power in the dyno, you could subtract the difference and go, this is what it costs to turn the engine.
Yep.
So this particular one had a racing 11, I think that was 11 quart.
Yeah,
weapon.
it's a big wet sump engine with a big giant 11 quart road race pan.
Yeah, which is generally a good thing, right?
Right.
And so, but what we decided is let's see what the minimum amount of oil we could run in the engine was. And I think we started out with about 5 or 6 quarts.
5 quarts of oil. Yeah.
Okay, 5 quarts. And then we did a run. And of course, you could see the oil pressure start to drop off.
Had the heart attack moment about
Yeah.
6,200
I'm running the
RPM. It
dyno,
goes,
and he's going, stop.
just going,
And I was like, I know, but it wasn't at 0.
it wasn't 0, but it was headed that way.
So anyway, we said, well, let's put 6 quarts in it. So we do that, and we do the run. Anyway,
It got a little better.
you have to remind me, I think, so the difference was it cost about...
About 15 horsepower, I think, for 1 quart of oil.
Yep. So then we're like, wow, that's interesting. Let's keep going. And let's just keep going until we don't lose oil pressure. And I think when we got to about 10 quarts of oil in the engine, the thing that was interesting is you could go over here and look at your combustion analysis and you go, this thing literally made exactly the same power, made within half a horsepower of exactly the same number with 5 quarts in the engine
Versus 9.
From
9. From 5 to 9.
Okay.
The in-cylinder power was within a half a horsepower, but we were down 60 on the dyno.
Now, in fairness, we were down 60 at 7,200 RPM.
Yes.
By the time we got to 9,200 RPM, it was down almost 100 horsepower.
Right.
Keep in mind, your combustion power, the fuel you're using, the air you're pumping, it's all the same. It's how much you paid to get that out to the crankshaft. And so the idea that you could use combustion analysis for a tune-up is a great thing in a systems-based approach. But all of a sudden you realize there's all these other things in the engine that are happening. I'm thinking about headers. What are you thinking about?
Oh, yeah. Well, yeah. So there's a couple of great stories. We had so much fun that week, it was ridiculous. It should have been illegal. All right. So we'll go with the headers first, right? We'll go with the headers.
Yeah, so one of the things we looked at right away was Billy's talking about this pumping loop, right? And so what you're looking at is just 4 of the 8 cylinders there. The first thing you notice is that the loops where the adiabatic compression and expansion are happening, they're fairly similar, this top side of the loop. But look at the difference in the pumping loop between the cylinders. And I assure you that difference was about the same amount going from one side of the engine to the other as well. And I think, if I'm not mistaken, do we have all 8 cylinders up there? Yeah, we do. We just have them paired up. So you can see that there's a dramatic difference in the pump loop between cylinders. And so we looked at each other and we're like, well, geez, that means this thing needs like a longer header or a shorter header. But it's different on both sides of the engine. So we got this idea. I said, hey, we had some short headers on the thing. And I told Lake, I said, I got some long tube headers out in the storage. Let's get them out and put them on the dyno. And he goes, no, let's just do one of them.
Yeah.
And I was like, what?
Short tube one side, long tube the other. Now, the thing with this way this cam was, it was a blower cam because the engine's built for boost. It's got this really weird dip in torque. It was around like 35,
no,
4,000 RPM.
It was right around between 48 and 5,200.
Right, it was this big dip, right? And we're like, okay, so we decided we're going to run short one side, long on the other. We put it on there, and it fills in half the damn dip.
Yep.
We were like, wow, that was cool. Of course, what do you think? Well, right. No.
You have the most common answer, just not the right one, Ron.
We were all just gobsmacked. We were like, what? Wait, now we got to flip it.
Yep.
We're like, okay, that's the problem, right? We said we have long tubes on both sides, and it did nothing. Invert it, go back, went right back to where it was before. It did not care what length header was on the right-hand side of the motor,
Yep.
but it cared a lot about which one was on the left-hand side.
So what that told us was we needed to look closer at the loops, right? So you could see very clearly that the exhaust system was talking to the intake system, right? And so Billy, we talked about this a bunch, where you can make a change in one part of the engine thinking this is going to be great, and all of a sudden you've made something else in the engine so mad that it offset whatever gains you might have had there.
Yeah, what we talk about is volumetric efficiency is basically how well the cylinder feels compared to the atmosphere around it. So 100% means that you have the same pressure, average pressure at bottom dead center. When you close it's bottom dead center, when it's trying to fill out, you've got the exact same pressure as you have in the atmosphere around it. That a 350 cubic inch motor moved 350 cubic inches of air every 4 strokes, every 2 revolutions. But we all know in this world, like if you go back in the 1930s and you told somebody, well, what's the best V you can get? They'd say like, well, maybe 50%, But we all know in this room that like 100% is easy, 120% is possible, and 130 might even occur. So even on normally aspirated setups. So the reason that you can get that is you've got to get that energy from somewhere. And people go, oh, well, wave tuning, you can intake, wave tuning and exhaust. Really, to get wave tuning, you have to use, where do you have the most pressure to valve event? It's exhaust valve opening. You've got this tremendous pressure right back in here, like we're looking at pressure here, right? So right in here we open the exhaust valve. My other event's like here, here, and here, but this one's way up here. I mean, it's a logarithmic curve, so a little bit change is a great big change. That's like, that's like 2 or 3 psi, maybe 4 or 5. I mean, that could be 20 psi or 30 psi. So you've got all this pressure here. So you use that pressure to create this wave going down the exhaust port. This wave, high pressure wave comes out, reflects the negative, low pressure wave comes back. And you can get, we see sometimes during this overlaps setup that you can see 5, 6, 10 psi difference trying to drive the intake in because of this low pressure. But the thing is that there's all this chaos. But this is where your volumetric efficiency can get bigger. Sorry.
Yeah, and so you alluded to something earlier. Go back just for 1 second there. You alluded to something earlier, and we talk a lot about where should we close the intake valve. And so this is another tool that tells us that. When you look at that slope, what's going on there across bottom dead center, when that piston comes to a rest and it's not moving, we are very much dependent on that incoming column of air that we call wave tuning or whatever.
Well, and the inertia too, right?
It's got momentum and inertia that's happening there. And so we pay a lot of attention to how much lift do I have at bottom dead center? What's my opportunity to continue filling the cylinder? If you close the valve too early, you've given away some opportunity. If you close the valve too late, then you wasted all this work you just did. And so, Billy, you talked about that slope there. Point that out again. And
like right in here, you can see at each of these, like we can use this slope coming up. If this line goes up and then back down, we know that we've closed the intake valve too late on this cylinder because we could have grabbed more air. That means when this comes down toward this line, if it goes past this line and back down, it's actually pushing air out that it could have burned. Now, other times you see, like on this cylinder, this one probably had the intake close a little bit too early because it was trying to slope up to it. So we can use the slope here as it goes to this straight line. How's this thing going? Is it overshooting? Is it undershooting? We can use this to change the intake closing on each cylinder of the engine. Now, this is like top secret NASA poo when it comes to NASCAR guys. But now it's something that you're starting to see with the NHRA guys and stuff. And it's where you can get, if you're able to grind the cam with a different camshaft design on each cylinder, you can do some pretty cool stuff in here. And it's, like you said, it's not about making each cylinder the same. You can't do that. It's like a football team. You can't make your linemen into wide receivers.
I thought it was more like teenage girls, so you couldn't get an 8 degree on anything at the same time.
I'm not even going to talk about that. My baby girl, okay. My daughter's going to become an attorney. She will sue me. Yeah. So let's not go there.
I have 2 daughters. I'm good. I'm safe.
The boys, we'll put them out. It's trying to help each cylinder do the best it can. And this is the thing, and I'll give a shameless plug to Ben, like the people who've been able to work with you and have you do spintron testing and have you do some of the tuning at your place. I know it seems kind of expensive, but there's really no other place in the world where you can get some of the stuff done like you guys do at EFI University. So thank you.
Yeah, no, especially at a commercial level, right?
Right, exactly. It's something that at a OE level, everybody does it. At the NASCAR level, everybody does it. It's like, how many people are wearing socks? It's like, okay, that's how many people are tuning each cylinder in NASCAR land, okay? So, so nobody sue me or anything for saying that.
All right, so Billy, we're at 2:00. Surprise, surprise, we were going to go over. Who expected that to happen?
Inconceivable.
Right. So
Keep using that word.
you got to do your sanity
That's what
check,
you
Billy.
think. Hey, no, this is kind of my favorite slide of the whole thing. And basically, as you go through here, you're going to be able to go through the PRI show, and you'll find stuff that'll pick up different horsepower. I went through one time and figured out I could make about 12,000 horsepower on a small block Chevy if I used the right spark plugs, air filters, motor oil, everything like that. When you look at engines, if I could leave you with anything from this presentation, is to look at to have this in your mind when you're looking at an engine. If somebody says that you need to make a certain amount of horsepower, you've only got 4 knobs you can turn. That's it. That's all there are. You can make the engine bigger, your displacement. So I've got my little knob over here from 200 to 800 cubic inches for Kazi. And so you can turn the displacement up and down, right? Then you got your engine RPM over here, and I went ahead and put 12 and 13,000 down there for Ben. But you can, what RPM you're running, yeah. So then you have your volumetric efficiency. We talked about that. How well is it filling each time? So each time you pull around. But then the thing, like they were talking about with the oil, they didn't change the displacement RPM or volumetric efficiency when they added more oil to that pan. And even they weren't doing the one that I love. Like I love combustion science. I mean, if you ever want to get me to geek out, talk about burn rates and how things work and what's really going in the fuels and all the products and how the combustion goes around. My kid's getting his PhD in this stuff, so he's got me nerded out on it. But combustion efficiency is a waste, but in this brake specific, there's not just combustion efficiency, but there's all the frictions. So everything on your rings that are going on, everything that's going on with the oil and all this. So every time you're changing, if you're trying to make more horsepower, what I used to do when I was, really working pretty high up in comp, and people come with this widget that make more power, well, I'd tell them, well, why? Did you improve whatever? If it makes more power, I promise you it moved one of these knobs. If it didn't move one of these knobs, it didn't make more power. You just measured it wrong. So these are the only things you can do. You can increase it, but what's crazy is if you take this stuff and do all the math to it, which I love math and some people hate it, but I can take a displacement of an engine, the RPM, the volumetric efficiency, that will tell me how many CFM with those three that's using it, every time revolution. I can take the CFM and go to mass. I can take the mass per minute, go to mass per hour. Then I can look at the air fuel per hour and I know, okay, how much fuel is it moving? If I know the brake specific, I can come with the horsepower. And I got in so much trouble with this deal because I don't know if you guys remember it, but I got my internet cut off at work because Motor Trend did an article on the news vet that came out, and they said that it made something like 700 horsepower on the chassis dyno, and I'm like, no, it didn't. And so on Facebook, me being the Billy, I just put out on Facebook all this, and I told them exactly what power it would make at what RPM and stuff like that. And there was probably a meeting at GM where they analyzed my numbers and I promise you, this stuff's really right, like within 1%. And not only, and what's funny is that this is how you make power. There was no way that if you were going to be, what was your volumetric efficiency? And I put 90, and I was off a little bit. It's a little bit higher than that. But the volumetric efficiency with something that has to pass emissions, you're not going to make it 120% because you can't have that much overlap. Brake specifics, you're going to have to run a little rich. You're going to have to, you can't run it, the catalytic converter's not going to let you run it real lean, so you can't be, these are the brake specific numbers you're going to have within a few percent. And you can go in here and figure out what you're going to make for horsepower. If you're going to make more horsepower than that, you've got to move one of those numbers. And, and that's something that if anything that I can give you, I know that sounds so simple to some of you guys in here, and you probably want to wring my neck for saying it. But honestly, this is something that's life-changing. If you can figure out, I've got to make it do something different to make more power, it will change you how you approach it, because you'll approach every system in your engine trying to figure out how am I going to twist one of those darn knobs.
And when you put it all together, you can make some big power.
Absolutely.
Yeah, that's what's fun, is you can really make some big gains when you start putting it all
right, because
together.
You're not just out there hacking anymore. If you take
You're
like
not
a golf, you're not a golfer that's coming out there just whacking at stuff. You've actually tried to develop your swing, and my knees are bad, and I can't do that. But you're really practicing your art. You're learning how to do something right, and it will change your deal, and you will give you a competitive advantage.
Yeah, I think what you find is when you get near some of the most well-developed engines on the planet, you find that rarely is there ever one single trick of the week part that revolutionizes things. More often than not, you change that one trick of the week part and it makes it worse because it wasn't really a part of the system. And so if anything you take away from this today, think about the engine as a series of connected and interdependent events. You cannot change any one thing and not have results both positive and adverse. So the question is, where's the trade-off? Was it worth doing that or not?
Right, and I don't mean any disrespect to anybody down there in the trade show, so don't take it as this, but when you're going through there and thinking about your engine, don't be looking for the part that's going to be the magic part. Be looking for the part that's going to work with your system, or you can develop your system around to make it all work together better.
It's the difference between being a chef and being a cook. Right? You want to think with that chef's mentality. How can I use what resources I have to make something different, unique, and better, not just banging out the recipe and repeating it, hoping it's going to be different. So hopefully that was enjoyable. It wasn't a waste of your hour, was it? No. Oh, good.
You're welcome for getting to sit down and get your feet off, because I can tell you standing up for like 3 straight days will wear your feet out and make
it hurts.
Make a grown man cry.
Any questions or anything before we go?
Is there anything available to break in an oil rail so it doesn't scratch a cylinder block?
Okay, so we're actually working on that. So getting away from chrome, because your only options you had, especially for guys who had nickel stuff, like the power sport stuff like that, you can't run chrome because there's nickel and chrome, and nickel tend to weld together.
It likes nickel.
Yeah, it likes that, so that's a bad thing.
They mate.
So, but then you've got this, steel rail, so it's going to wear quickly. So if you put like a CRN coating on, or a DLC even, the problem is it applies at such a high temperature that it waffles the rail. It basically turns it into a rinky-dink. So we found a low temperature titanium nitride, which is that gold, right? So anybody that does any machine work, got a gold drill bit, gold insert, what makes that thing work good is the titanium nitride coating on it. We have a low temp tie that we're currently testing on the oil rail. So now you don't have those bumpy lumps like your 57 Chevy chrome bumper. It's now thin, it's PVD applied. It actually helped pick up some horsepower, which was not the goal. It was just, hey, get rid of the streaking. So we are working on that. It's not ready for sale today, but we've been testing it in the last month and a half.
It's part of the R&D.
It's part of the R&D, yeah. Which is great, because then you can run it in a small block Chevy, you can run it in a Porsche, you can run it in anything. It doesn't care what cylinder material it is. It's happy. Alusil, Nikasil, Sumabore, gray cast iron, it won't care.
Yeah, and you guys, we appreciate y'all asking questions, because we really y'all were just the guinea pigs on this whole presentation.
And
so there's no way we got it perfect.
They don't have a booth, but I got a booth. If I stay up here longer, that means I don't have to stand in my booth a little bit longer. So
yeah, we're just gonna run hide.
Yeah. What else we got? Yeah.
What are your parameters for your oil analysis? Like, how long do you run it on the dyno for? What's your standard?
Yes.
Well, the key is being consistent. Whatever measurement you're going to do, like if you run a dyno test and you're going to take oil samples from it, well, you need to do, if you're normally running an hour, you always need to run an hour. That way you have the same run time. Because it's not about the absolute values, it's about the trend analysis. I mean, taking one sample gives you one set of data. 1 point, and it's like a 1 pixel image. It's black, it's white. Oh, okay.
After 5 minutes, after 15 minutes, after an hour, after 15 hours, after 100 hours, and every interval you can think of at that. The more data points you have, the more you're going to figure out what is doing what when. One of the things we found break-in is that break-in, actually most of the break-in occurs on a flat tappet camshaft in the first 2 minutes.
Yep.
And we always say 30 minutes, right? But if you don't make it through the first 2 minutes, and be honest with you, if you could do something different, you might want a different oil chemistry with higher friction for the first minute or two, and then a different oil chemistry after about 5 minutes. But that would be a different chemistry than you want to ship the motor with. So you'd actually want to have, if they're well enough in time, there'd be 3 different oils you'd want over the first 30 minutes of a engine's life, but it's your money, not mine.
Well, ideally, you'd have 2 different oils in the engine at the same time.
Yeah. Okay. Yes, Larry.
There's another one over there, I think. Nope.
What's your question?
Yeah, I was going to ask about the volumetric efficiency at 120%. Are you, is that the total flow or is that the trapped mass?
That's the trap mass. So actually, it's more than 1.2 atmospheres when the intake valve closes. More like 1.4, 1.5, depending on how late it is.
How are you actually determining the trapped mass?
You know, that's an interesting deal. Yeah, it's hard to know for sure. The best way we can do it is to look at your fuel flow, because a lot of that fuel isn't going out the exhaust. So, you know, some of the times you can look at your fuel flow and your air fuels and try to figure it out. But most people would just look at total, so not the trap mass. But they are not looking at volumetric efficiency for the pressure at bottom dead center. You're looking at what actually got caught. You know what I mean? You're not looking at VE at the bottom. You're looking at VE in the intake valve closing. So yeah, it would be total airflow. I'm sorry, I told you absolutely wrong.
But the main question is, you were talking a lot about overlap, and then you mentioned on the stock cars not being able to use the overlap because of exhaust.
Yeah.
That implies that throwing a lot of overlap, you're just pushing a lot of air.
No, it's actually very, very, if you really look at the airflow at overlap, it's actually quite small. You know, that you're not actually getting, now I know being from Alabama, you don't get more snow than I do. But has anybody here actually where y'all live, some of y'all live where it snows, right? Well, when I was a kid, I got to go to Arkansas, and we had snow in Arkansas in the Ozark Mountains, and I lived on a hill. And on this hill, there was this tennis court, and we'd go out there and make a snowball. And you'd start the snowball, and you go over the hill, and you push it over. Now, somebody had a house down there, and they knew my parents. But you could take a snowball that was about the size of a grapefruit, and you could daggum near knock a wall off their house by the time it got down there. And overlaps like that, you're not trying to, I'm sorry for the crazy analogy, but you're not trying to move a lot of air with overlap. You're trying to build the snowball and get it rolling. And that's what we see with like this new low shock camshaft designs that we do. You know, we thought we had to open this intake super quick. Well, the problem with opening it super quick is there's a valve, the piston and valve don't like being in the same space and same time. Einstein didn't know he was talking about that with the whole space-time continuum, but really that's it, that the intake valve and piston don't like to share space and time. So the whole thing is, if you try to open it real quick, you're just going to go and hit the valve, and then it's going to make up the piston. It's going to mess up your brake-specific fuel consumption. So if I put this big pocket in here, my combustion efficiency is going to go to bad stuff, and you know, that's going to be a problem. So I can't put this big, probably going to lose compression. That's going to mess up everything. There's going to be a lot of things I'm going to do wrong with brake specific if I try to put this big valve relief. So I want the smallest valve relief I can get, but I need time to build this whole, you know, get this train rolling, right? Yeah. So if I can open the intake a little slower, a little earlier, and not hit the piston, I can actually give more time to build this thing up. And back to your question is, why does your snowball matter to me, Billy? Well, what we found out is opening it early didn't really flow any change volumetric efficiency. We weren't seeing more air go through because really, and you go back, and this is where modeling comes into thing. One of my good friends, Dan Agnew, is doing some engine modeling. He's trying to come up with a way to do it at the sportsman level. And so this is that whole thing that like NASCAR, everybody has really good 1D models of their engines. That's going to be something available to you guys in the next couple of years. And if anybody has any questions, just hunt me down someplace or find Dan Agnew and say, Billy said you do this. But, you know, what we're finding with the engine modeling is when we can get an engine model to match those PV diagrams and everything like that, which we can definitely do, we can get this thing and we can actually see what the port velocities are. And you would be, Paul, you'd be shocked how low the port velocities are during that overlap. And the reason it's not is, if you go back 3 or 4 slides, look at the pressures down here. There's not, what drives mass flow is delta P's. Mm-hmm. There ain't none during overlap here. You know, the pressure on the exhaust, I promise you, when the valves are open, the pressure on the port on both sides are the same as the pressure in the chamber, right?
Wait, hang on.
Pretty much so.
I can't help but think we're giving away too much about what we're going to do in January at the Expo, but we ran into with the Expo engine at high RPM because the problem was those almost went
They will.
opposite because
Yeah,
we couldn't get it out.
Yeah, your delta P goes the wrong direction. All of a sudden, you're on overlap, and you
Yeah.
can't make the exhaust work good
Yeah,
enough. so it just
in low
stacks up.
RPMs,
Yeah.
a lot of times you are absolutely feeding the other way. But it can actually help your overall power. Even if you open the intake, and instead of intake coming in, exhaust goes out. Well, it just goes out a little bit in the intake port, and then all of a sudden the piston starts coming down and goes right back in there. Well, you go, well, Billy, there's no way letting exhaust into my intake port could have possibly helped me at any RPM. Well, at low RPM, it might have helped you because you got plenty of port for it, right? Where's peak piston velocity? About 70 degrees after. There's only so fast you can open this door. So if I open that door earlier, I can have the door open wider at 70 degrees. So now I can actually suck more air in then. So you might actually have velocity the wrong way, no air go through, actually air go backwards during overlap, and it still increase your overall power. One of the things with my son's research at Georgia Tech is, you know, he has this closed chamber and he can change the chemistry of what goes in there. And like we always used to think carbon dioxide into the chamber, you know, exhaust into the chamber is really, really bad. And you'd be surprised when it comes to combustion efficiency, a little bit of exhaust in there. The EGR, the reason the EGR was bad is because it's just heating up stuff that didn't need to be heated up. It wasn't the fact that that exhaust in the chamber is going to really do all that bad stuff to it. So a little bit of leftover food on the plate's not such a bad deal.
What else we got?
Paul, did I do halfway okay? I know that you're like an academic and I'm just a bubba and I'm trying to sound like, okay. A minus, dude.
B
Dude,
minus.
B's get degrees. I'm like, what? Yeah.
Yes, sir.
This is a volumetric efficiency. With a port fuel injection, with the energy of the air and fuel in the cylinder, can you time the fuel injector to shut off slightly earlier to keep the anti-reversion energy at a lower level?
There is the amount of research that's done on fuel injector placement, angle, velocity, flow, upstream, downstream, up nozzles, down nozzles would fill up 10 seminars. But
The simple
yeah.
answer is probably not, though. Like
No, it won't do exact. It won't do. It's not as easy as you think it is.
Yeah.
Your
One
question
of the-
made it act like, man, there's just this one thing I could do and it would work. Sorry, Larry, it won't. But there's a whole lot in that deal that you can do. You know, playing with injector position and timing.
Well, I was thinking about the high-speed video
Yeah.
that we had. So one of the things you got to consider is the relationship of the size of the injector to the fuel flow requirement of the engine, right? So duty cycle is a common term that we use. So if you think about if I have a 50% duty cycle, what that means is your injector is spraying fuel for 360 degrees out of the engine cycle. Well, even if you have 260 degrees of duration on the camshaft, that's still 100 that you were spraying fuel no matter what. So when your duty cycle gets 70 and 80 and 85 and 90%, it's almost completely irrelevant because it's going in there all the time. So the reality is you'd have to have a very low duty cycle to be able to do that, which would require your injector to be so large relative to the engine's fuel demand.
In HRE per stock.
Yep, it's exactly. So we tried that, and when I worked at Elite, we tried that 100 ways to Sunday and where the injector was and which way you pointed it, and you know.
They call it poor man's DI.
Yeah. So the problem is your wide open throttle pulse width needs to be sufficiently small that its duty cycle then is smaller than the duty cycle of your intake valve, let's call it that, right? So figure, 260 out of the 720 gives you about 36% duty cycle of the intake valve. So anytime your wide open throttle fuel pulse width gets longer than that value, you're going to be spraying with the valve closed anyway. If you get the injector large enough to make it inside that window, what happens is now it's difficult to make the thing idle because you're down to such tiny little opening times, and the dead time or the offset of the injector gets critical in that. So it's theoretically possible. It's just way harder in practice.
And sometimes it does a mess to you because when you have dry air going in, you're losing momentum. If you looked at like the F1, they used to have the up nozzles and the down nozzles. And the reason you have the up nozzles, still do it in the sprint cars. The reason you have the up nozzles is you're cooling the air charge coming in, but you're also adding to the density because this has mass. So if you're not port limited, now if you guys have, your port can't be much more than this cross section, running just air through it's great. But if you're unlimited on port cross section, adding fuel to it, remember we talked about that with that all that velocity when it's coming up and everything, the momentum closing the intake later. When you just go air without fuel in it, it's much lighter. So especially if you're in alcohol where it's so much fuel into it. But that momentum, not only does it cool the air, which makes it denser, which you can put more in there, it also adds more momentum, which will let you fill longer past bottom dead center. Yeah, you just, there's a lot of velocity there, and I'm not sure you want to take energy away from that reversion. I just really not. Now, at the RPM where you're making between peak torque and peak power and above peak power, there's almost no chance that you've got real reversion there. Like, notice I talked about reversion being good for you, and I gave all these examples for low RPM. If your header link's right, you don't have reversion at the operating speed. It's pulling on you.
You also need time to atomize or to vaporize the fuel, depending upon what fuel you're using. If you're restricted on the fuel, NHRA Pro Stock, you will be in trouble if you try to shorten that time up because you have a fuel that doesn't want to evaporate. Your injectors can atomize, but that doesn't mean it's vaporized, and it won't burn if it's not vaporized.
Well, before we win the award for longest presentation of PRI, we should probably wind down, but we want to leave you with the idea that it is a systems-based approach. One of the concepts that Lake and I have been talking about lately is, we forever have thought about, an engine with equal length headers. And what we've learned nowadays is really that's probably the last thing the engine wants. Mm-hmm. It's 8 unequal cylinders. They could use 8 unequal camshaft timings. They could have 8 unequal headers, so whether that's an 8-cylinder, a 12-cylinder, a 16-cylinder.
Different runner lengths.
Yeah, absolutely, yeah. So at the end of the day, we want you to be thinking about the whole entire big picture system when you change one component. That was really the gist of the whole concept for the seminar, I would say.
Yeah, and we really want to thank PRI for having us up here, and Lake trapping us up here. And just for your time to sit through this, we appreciate more than you know. I hope you got some things out of it. When I went to every presentations, I'd think, man, can I take 1 or 2 things out of here? It doesn't have to be every word we said, and I say way too many. Just go in there and see if you can think about this over time and see if there's ways that you can use it practical for your system. We'd really appreciate it.
So the good thing is, after about a year, they forget about this and we get to do it again. I can rope them back in again every couple of years. They forget about it.
Yep, that's right.
No, but seriously, thank you all for coming and taking the time. We really, really appreciate it.
Very cool. Thank you, guys.